just referenced tools in a book. Can everyone hear me just fine? I had to redo my configuration down here, so I just want to double check before we continue. Just type yes in live chat if you can hear me. Anyone? Awesome. Thank you. All right, we'll start in about a minute. All right, howdy. So, today we are going to be talking about linear dependence. So in order to lead up to this, I kind of want to give a brief review of what we did on Friday. So, we'll start with that. So up until last class, we had been talking about linear systems, and then we've been talking about determinants. And now, for a little bit, the focus of this course shifts, and we start talking about things from a more abstract perspective. And the thing I was talking about on Friday was vector spaces. So I'll recall the definition. A vector space is a special kind of set. Namely, it's one that satisfies the following 8 axioms. So axiom A1 guarantees that addition is commutative. Axiom A2 guarantees that it's associative. And other than having an addition operation on the set, you also have an operation called scalar multiplication. And all 8 of these axioms are satisfied. For example, A4 here tells you that whenever you have an x in your vector space, there is a negative x in V, such that if you add the vector plus its negative, you get the 0 vector. And if you add the 0 vector to anything, you just get the vector back. So these are the axioms of a vector space. And not only did we talk about what a vector space is, we introduced another notion that's equally important, which is the notion of a subspace. So a subset of a vector space is said to be a subspace if it is closed under addition and scalar multiplication. And then, for the remainder of Friday's lecture, I talked about all the different ways that you can construct a given subspace. So, a few stand out, namely, well, the most important one for us today is the notion of a span. So I want to recall that as well. But the idea is that if you have like some collection of vectors, like say v1 through vn, you can look at all possible linear combinations of them. And it turns out that the set of all such linear combinations forms a set called the span, and this span turns out to be a subspace of the vector space V. Now, I will have more to say about this soon. In fact, all of basically today's lecture is going to be about studying various aspects of spans. But before I get to that, I want to finish off one little bit of business from last lecture that I didn't get to. So here is a nice result on null spaces. So let me just recall it for you. What is a null space? Given a n by m matrix A, then the set of vectors V inside Rn, actually Rm, with A times V is equal to 0, form a subspace of Rm. And we call it the null space. And denote it by n of A. So that's what the null space is as we defined it on Friday. And next we have the following theorem about null spaces. So this is a theorem about finding solutions to linear systems. Now, suppose we have a linear system AX equals B. Suppose it's consistent and that x naught is a particular solution. Then a vector y will also be a solution if and only if y equals x naught plus z, where z is an element of the null space. So because we have if and only if here, we have two directions to prove. So let me start by proving the if direction. The sufficiency direction. So suppose y is equal to x naught plus z, where z is in the null space. Then A, the matrix A applied to the vector y, is the same as the matrix A applied to x naught plus z, which by linearity of matrix multiplication is the same as A applied to x naught plus A applied to z. Now, by our assumption that z is in the null space, we know that A times z is equal to 0. So this is actually just the same thing as A applied to x naught plus 0. Add 0 to anything, you get your thing back. So this is A applied to x naught, which by assumption x naught is a particular solution to this equation, so it's just equal to B. So whenever you take your particular solution and you add to it anything in the null space, you get yet another solution. Now let's prove the only if direction, which is the necessity condition. So suppose x naught and y naught are two solutions of ax equals b. Then what we can do is we can consider A applied to x naught minus y naught. By the linearity of matrix multiplication, this is the same thing as A applied to x naught minus A applied to y naught. And we know that both of these are going to be equal to B because we've assumed that they're solutions to this equation. So this is equal to B minus B. The two B's here cancel, and we're left with 0, which means x naught minus y naught is an element of the null space of A. So x naught is equal to y naught plus z naught for some z naught in the null space. And this completes the proof. So having a single solution of your linear system and having a complete description of the null space of the matrix A, in fact, gives you a complete description of all solutions to this equation. And that's the power of this theorem. And this is used over and over again at various levels of generalities. One area it comes up, for example, is in the theory of ODEs. Now, I just want to kind of sketch why it's so useful. Consider the following two differential equations. Y double prime plus y is equal to 0, and y double prime plus y is equal to cosine of x. This is called a homogeneous equation. And this right here is a non-homogeneous equation. So I'll call this 1, I'll call this 2. And here's the thing. If g of x is a solution of 2, then the set of all solutions to 2 is g of x plus f of x, where f of x is a solution to 1. So this is a generalized version of the previous theorem. The reason this is so is because solving this equation right here basically morally, and not morally, in fact exactly, corresponds to finding the null space of a certain matrix. And whereas right here, this is a non-homogeneous equation because you have something non-zero on the right side. But if you can find a single solution to it, and you can find all solutions of the homogeneous equation, then you can take them together and you get all solutions of the non-homogeneous equation. That's the power of this theorem. And it's used over and over again in different areas of mathematics, and we will use it throughout the course. Anyways, now I want to move on to talking about span again. So let me just set this up so I can see what you guys type occasionally. Maybe I'll do that. Okay. So I want to talk about span. And I want to look at two different examples. So here's one example. What if we look at the vectors E1, so this will be the column vector with 1, 0, 0. E2 will be the column vector with 0, 1, 0. E3 will be the column vector with 0, 0, 1. Now, if you haven't noticed, I've used this particular set of three vectors several times now. I used them in the Friday lecture as well. In fact, whenever they come up, I may just refer to them as the standard basis of R3. And later today, I hope to define for you guys what a basis actually is. But just to avoid repeating myself or rewriting the same thing too much, I'll just refer to these things in the future as the standard basis. It's what it's usually called anyway. So I want to consider these three vectors and then another vector as well, v. So here v will be the vector 1, 2, 3. Now, as we observed last time, the span of E1, E2, E3 is already equal to all of R3. Hence, we have to have that this is equal to the span of E1, E2, E3, as well as the vector v. So in some sense, adding the vector v to this list here doesn't give us anything new. But it does tell us one thing. namely that this vector v can actually be expressed in terms of these three vectors. In fact, we have 1 times e1 plus 2 times e2 plus 3 times e3 is equal to v. And this is the same thing as 1 times e1 plus 2 times e2 plus 3 times e3 minus v is equal to 0. This is a relationship between all three vectors that appear in this list. And what we kind of want to do now is we want to get in the business of characterizing these kind of relationships. So I'm going to state a result and prove it, and then give you guys a definition to give you some understanding of how this works. So here's our theorem. So let me put it up here. This theorem is going to have two parts, 1 and 2. 1 says if v1, v2, blah, 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 all the way through vn span a vector space v, and one of those vectors can be written as a linear combination of the other n-1 vectors, then those n-1 vectors span v. And part 2 says given n vectors, v1 through vn, it is possible to write one of the vectors as a linear combination of the other n-1 vectors, if and only if there exist scalars, c1 through c2 not all 0, such that when you add c1 times v1 plus c2 times v2, blah, 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 plus cn times vn altogether, you get 0. So this is the theorem, and I'll prove each of these parts individually. So I'm going to start with a proof of 1. All right. So suppose after maybe relabeling, that we can write Vn, the last vector in this list, as a linear combination of the n-1 vectors before it. Then this is going to be equal to alpha 1 times v1 plus alpha 2 times v2 plus blah, 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 alpha n-1 times v n-1. So what this tells us is that Vn actually lies in the span of V1 through Vn-1. Now, suppose W is also an element of the span, or I'm sorry, I want to actually assume that W is an element of the span, or W is an element of the vector space V, which is the span of all the things. So V1 through Vn. Then what we can do is we can write W as beta 1 times V1 plus blah, 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 beta n times Vn. Now, the key observation is that we can combine this relation with this relation. And the reason we can do this is we can simply replace Vn here with this expression of Vn. And if we do that, then it turns out that we can write W as alpha 1 times V1 plus beta 1 times alpha, wait, let's see. So I'm replacing Vn here. I'm replacing Vn here with this. So I'll have beta n times alpha, actually I don't. Beta n times alpha 1. Hold on. Let me get rid of that. And now this is correct. So this is equal to this times this, plus alpha 2 plus beta n times, sorry, I messed up again. Beta 1 plus beta n times alpha 1 times V1 plus beta 2 plus beta n times alpha 2 times V2 plus blah, 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 all the way up to beta n minus 1 plus beta n alpha n minus 1. Let me give myself a little more space. Actually, I'll just put this here. Vn minus 1. Oh, that's unfortunate. I can just move it. That's better. Times this, times V, n minus 1. Okay, so what I've done here is I've combined this relation with this relation to re-express my arbitrary vector W in terms of the vectors V1, V2, and Vn minus 1. This shows that W is actually in the element of the span of V1 through Vn minus 1. And because I did this for an arbitrary vector W, this shows that the first n minus 1 vectors of this list actually already span V. So that completes the proof of 1. Now, let's do the proof of 2. So what we have to do is we have to show that given n vectors, v1 through vn, it's possible to write one of the vectors as a linear combination of the other n minus 1 vectors, if and only if there exist scalars, not all 0, such that c1 times v1, c2 times v2, plus blah, 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 cn times vn is equal to 0. This is easy, or at least one direction is. So here's what we learn. Suppose that we can write, say, as before, after possibly relabeling, Vn as alpha 1 times V1 plus alpha 2 times V2 plus blah, 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 alpha n minus 1, Vn minus 1. Well, then this is the same thing as 0 is equal to Vn, actually, I'll write it like this. Alpha 1 times V1 plus alpha 2 V2 plus blah, 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 alpha n minus 1 times Vn minus 1 minus Vn. Note that not all coefficients here are 0 because particularly the coefficient of Vn here is negative 1. So if we have this relation, we easily get a relation of this form, where not all the coefficients are 0. So this completes one direction of this proof. The other direction of this proof is to suppose that we have a relation like this already, where not all the coefficients are 0. Then we should be able to express one of the vectors in terms of the other n-1 vectors. So for the other direction, we're going to suppose, for simplicity, and by this I mean we can kind of relabel things appropriately, that Cn is not equal to 0. We know that one of these coefficients has to not be 0. And I'm just saying, okay, let's relabel or re-indexing so that Cn is the one that's not equal to 0. Then, if we have C1 times V1 plus C2 times V2 plus blah, 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 Cn times Vn is equal to 0, what we can do is we can just move the Cn, Vn to the other side, and we get Cn, Vn, or I shall move all this to the other side, is equal to negative C1, V1 minus C2, V2 minus blah, 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 minus Cn minus 1, Vn minus 1. And now I can use my assumption that Cn is not equal to 0 to divide this entire relation through by Cn. And I find that Vn here is equal to negative C1 divided by Cn times V1 minus blah, 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 Cn minus 1 divided by Cn times Vn minus 1. And I've now expressed my vector Vn in terms of the other n-1 vectors. So it turns out that whenever you have a relation like this between your vectors, and not all of these coefficients are 0, then you can express one vector in terms of the other n-1 vectors. But it also goes the other way. If you can express one vector in terms of the other n-1 vectors, then you get such a relation. And so this completes the proof of our theorem. Now this motivates the following definition. And this is going to be a very, very important definition for us. Given n vectors in a vector space, v1, v2 through vn, we say they are linearly independent if c1 times v1 plus c2 times v2 plus blah, 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 Cn times Vn is equal to 0, implies that all of these scalars must themselves be equal to 0. And likewise, we shall say that they are linearly dependent if we shall say that they are linearly dependent if there is a relation C1, V1 plus C2, V2 plus blah, 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 Cn, Vn equal to 0 with not all Ci equal to 0. So this is the notion of linear independence and linear dependence. And if you have n vectors in a vector space, this is a dichotomy. So either your vectors are linearly independent or they're linearly dependent. Exactly one of the following statements has to be true. Okay, so let's give our first example. Consider the vectors 1, 3, and 2, 4 in R2. What we want to know, are they linearly independent? So how can we figure this out? Well, what we can do is we can consider the following equation. C1 times the vector 1, 3 plus C2 times the vector 2, 4 is equal to 0, 0. This is the 0 vector. And what we can try to do is, given this equation, we can try to figure out C1 and C2. If we can find C1 and C2 that are not both 0, then they're linearly dependent. But if we can't find such C1 and C2, they're linearly independent. So let's unravel this a little bit. This is actually, or at least this thing right here, is the same thing as C1 plus 2C2. And this thing down here is the same as 3C1 plus 4C2. And we're demanding that this is equal to the vector 0, 0. So this is the same thing as the linear system. C1 plus 2C2 is equal to 0. 3C1 plus 4C2 is equal to 0. And of course, we can understand this as a matrix equation, where the matrix is 1, 3 in the first column, 2, 4 in the second, C1, C2 is getting multiplied by it, and this is going to be set equal to 0, 0. So why don't we call this matrix right here A? So now we've translated our original problem of asking if something is linearly independent to asking something about a matrix equation. The upshot of doing this is now we know how to solve matrix equations. So we can use what we know about solving matrix equations to kind of analyze this. So, if A has an inverse, we can multiply both sides of this matrix equation by A, and we would find that C1, C2 is equal to, are both equal to 0. But if A doesn't have an inverse, this equation will have non-trivial solutions. It'll have, or in other words, A will have a null space. So to analyze whether A has a null space or not, what we have to do is we have to look at the determinant of A. So the determinant of A is going to be equal to 0 if and only if, or actually I'm going to say is not equal to 0 if and only if the null space of A is equal to 0, the 0 subspace. So, in order to answer our question, what we need to do is we need to compute the determinant of A. Well, the determinant of A here is 1 times 4 minus 2 times 3, which is exactly equal to negative 2. This is not 0, so the null space of A is 0, which means that C1 and C2 have to both be equal to 0. So these two vectors in R2 are linearly independent. That completes our first example. Now let's do another example. Let's consider the following vectors. x1 is equal to the vector 1, negative 1, and 2 at the end. x2 here will be equal to the vector negative 2, 3, 1. And then x3 here will be equal to the vector negative 1, 3, 8. And these are all in R3. All three vectors are in R3. And the question we have is, are they linearly independent? So the approach we're going to take to this is the exact same approach that we took here. But I'm going to kind of omit some of the steps, and I'm going to jump straight to the matrix equation. The relevant matrix equation here is the matrix that has 1, -1, 2 in the first column, -2, 3, 1 in the second, and -1, 3, 8 in the third. And it's being multiplied by C1, C2, C3, and we're setting it equal to 0, 0, 0. And the question of the linear independence of these three vectors is exactly going to correspond to whether there are non-trivial solutions of this matrix equation. And the existence of non-trivial solutions, in this case, corresponds to whether or not the determinant of this matrix is singular. So what we have to do is we have to analyze the determinant of A. Okay, so here's how we do that. We're going to do a cofactor expansion along the first row. So we'll have 1 times the determinant of 3, 3, 1, 8, minus -2 times the determinant of -1, 2, 3, 8, and then plus -1 times the determinant of -1, 3, 2, 1. And so now I have to evaluate all of these things, which is a little bit tedious, but we can do it. So 3 times 8 is 24, minus 3 is 21. It's getting multiplied by 1, so I have a 21 here. Let me just draw a separating line. Here I have -1 times 8, and then minus 6. So that is precisely going to give me -14. And then it is minus 14 times plus minus 14 times +2, so plus -24. And then finally we're going to have minus -1 times 1, so it's -1, and then minus 6, so minus 7. So here, if we added this and this together, we get -31. -31 plus 21 is simply -10. So the determinant of this matrix right here is not equal to 0. Which means that this has a unique solution. So, and that unique solution is C1, C2, C3 is equal to 0, 0, 0. And so these three vectors are, in fact, linearly dependent. Okay. So, let me just double check myself real quick on this. No, this looks right. Okay, so let's do another example. I want to look at the vectors x1, 1, 5, negative 2. x2 equals 1, 3, 2. And x3 equals 3, 11, 2. So let me stare at this just for 1 second. Yeah. I want to know if these three vectors are linearly independent. And I'm going to go through the same process and set up the following matrix equation. So 1, 5, negative 2, 1, 3, 2, and then 3, 11, 2 times C1, C2, C3, all set equal to the 0 vector. And I want to know if there's a non-trivial solution to this. So A times C is equal to 0. As before, I can answer my question by computing a determinant. And the determinant of A here is going to be equal to 1 times this cofactor, 3, 11, 2, 2, minus 1 times this cofactor, and then plus 3 times this one. So I think I set this up correctly. So now I have to do a little bit of computation. Right here we have 3 times 2 minus 2 times 11, so 6 minus 22. That is going to be negative 16. So 1 times negative 16 is just negative 16. Over here we're going to have minus 1 times 5 times 2, so that's 10, minus, or actually plus 22. So we're going to have 32 here. And then we're going to have plus 3 times, let's see what we get here, 5 times 2, which is 10, plus 2 times 3, because of the negative sign. So I get 11, so plus 3 times 11. Now, did I do this right? Oh, no, I'm sorry, this is 16. 5 times 2 is 10, plus 6 is 16, so plus 3 times 16 is going to be equal to 0. So the determinant of this matrix is 0. So this equation has a non-trivial solution. So these three vectors are in fact linearly dependent. So no, they're not linearly independent. And so the next question you probably want to ask sometimes is, if your vectors are not linear independent, how do you find a linear dependency relation between them? So in order to do this, what we're going to do is we're going to take our matrix equation and we'll state our problem precisely. So given that x1, x2, x3 are not linearly independent, how do we find a non-trivial linear combination of them? Equal to 0. Okay. Well, what we can do is we can use techniques that we learned in the first week of class, namely row reduction. So if I take this matrix right here, And this is really all I need. And it's somewhat hard to select. We can study it. Note that applying row operations corresponds to multiplying by elementary matrices on the right. So basically what I would do if I'm applying a row operation is I'm taking this equation right here and I'm multiplying it on the right by a matrix E. So I would have E times A times C is equal to E times 0, which is just equal to 0. So as I'm applying row operations, I never actually change this C because all that's happening is on the right. This is very useful. And the reason this is very useful is watch what happens. I can apply first off the following row operation. I can set row 2 here to be equal to row 2 minus 5 times row 1, and I can set row 3 here to be equal to row 3 plus 2 times row 1. And if I do that, I'm going to have 1, 0, 0 here, 1, 3 here, and this row and this row are going to change. So I'm subtracting 5 times 1 from 3, so I'll have a negative 2 here. I'm subtracting 5 times 3 from 11, so I will have a, so 5 times 3 from 11, I'll have a negative 5 here. Wait, no, I'm being an idiot. Of negative 4. And then I am adding 2 times row 1 to this. So I get 0 here and 4 here. And then 2 times 3 plus 2, I get 8 here. Okay. Now I could do more row operations to this, but I don't really need to. Because let's see what has to happen. If I multiply C1, C2, and C3 by this matrix, what you see is that you have to have particularly 2 times C2 plus 2 times C3 has to be equal, or I'm sorry, plus 4 times C3 has to be equal to 0. Now, this corresponds to the fact that if I row reduced further, I would have only 2 free variables, C1 and C2, and C3, or I'm sorry, I would have only 2 bound variables, C1 and C2, and C3 would be the free variable. You can see that as I can just use this row right here to cancel out this row by multiplying it by 2. So what I'm going to do is I'm going to set C1 here, I'm going to set C2 here to be equal to 2. I'll set C3 here to be equal to negative 1. And you can see that for this choice of C2 and C3, this equation is satisfied. Now, let's look at our final equation, namely this one. Or at least, yeah, that. If I multiply this column by this row, I'm also going to have the equation C1 plus C2 plus C3, or plus 3 C3 is equal to 0. Now I've chosen C2 and C3, so I have to have C1 plus 2 minus 3 is equal to 0, which means C1 plus negative 1 has to be equal to 0, which means C1 has to be equal to positive 1. So now I've actually found a non-trivial solution to this linear system. And we can write it down over here. the vector 1, 5, negative 2 times 1 plus 2 times the vector 1, 3, 2, and then minus the vector 3, 11, 2, is equal to 0. Or actually, I'll just say this is the 0 vector. So, using row reduction, I'm able to obtain specifically a linear dependence relation. Note that by our first theorem of the day, this is the same thing as expressing the vector 1, 5, negative 2 as 3, 11, 2 minus 2 times 1, 3, 2. So, this is how we actually find linear dependence relations. Okay. So I want to give another example, one that's really interesting and comes up in a lot of situations. But to do that, I have to define a vector space for you guys that I haven't exactly defined yet. So last class, I talked about C of A, B. And C of AB was, of course, the set of continuous functions f from the closed interval AB to the real numbers. And as I stated last time, this is a vector space. And it's a very, very easy proof. You can go back and watch the last lecture for part of it. Inside this vector space, there's a very interesting subspace. And we say it's called Cn AB. And at first, it's the subset of continuous functions f from the interval AB to the real numbers, satisfying the following extra properties. F is n times differentiable. So I can differentiate the function n times, and all n derivatives are continuous. So, in fact, last time I considered the special case where n is equal to 1, but I can do it generally now. Then, Cn of AB is a subspace of CAB. Okay. So this is a very important subspace in the theory of ODEs, as we'll see. And what I want to do is I want to consider what linear dependence and independence means in this specific example. So, suppose f1, f2, blah, 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 through fn are all elements of Cn AB. And they are linearly dependent. Well, of course, this means that we can express the 0 function as a linear combination of these n functions. So we have C1 times F1 plus C2 times F2 plus blah, 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 Cn times Fn. And this is equal to 0. Well, because all n of these functions are differentiable, we can in fact take this relation right here and we can differentiate it. If we differentiate it, we'll note that C1 through Cn are constants, so the derivative is going to be C1 times F1 prime plus C2 times F2 prime plus blah, 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 Cn times Fn prime. And if you differentiate 0, you still get 0. But now I can keep differentiating. So if I differentiate again, I have C2 times F1 prime, or I'm sorry, C1 times F1 prime plus C2 times F2, or sorry, these are double primes now. C2 times F2 double prime plus Cn times Fn double prime, and this will also be equal to 0. And this has n derivatives, so, or these functions have n derivatives, so I can just keep doing this process over and over again until I get all the way down to C1 times F1, and here I will do the n minus 1th derivative plus C2 times F2, I'm taking the n minus 1 derivative of that, plus blah, 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 Cn times Fn, and I'm taking the n minus 1th derivative of that, and that's also equal to 0. So from my one linear dependence relation, I have produced a whole list of other linear relations obtained by differentiating. Now, the cool thing we can do is that we can regard this as a matrix equation. Where the entries of the matrix are the ith function and the jth derivative of it. So if I do this, I am led to the following concept. And this is the Wronskian. So in fact, I only need my functions to have n minus 1 derivatives. But it doesn't matter whether I take n here or n minus 1. This is just a slightly weaker condition, which makes it useful. If we have n functions in this space, we can define the Wronskian by arranging these entries in a matrix and taking its determinant. The Wronskian is a new function, and it's called, well, the Wronskian of F1 through Fn. And here's the key fact about it. This is going to be a theorem. If F1 through Fn are elements of this space, then there exists a point x0 in AB, and if there exists a point x0 in AB, such that the Wronskian is non-zero, then F1 through Fn are linearly independent. The reason this is true is that if they are linearly dependent, then we have to have that this matrix times this vector has to be equal to 0. And if that's true, then the determinant of this has to always vanish, because this matrix is always singular, regardless of which point x0 you take. So by using this fact, we see that linear dependence implies that the Wronskian has to be equal to 0 for all x. And so if the Wronskian is ever non-zero, we're able to kind of conclude things in the reverse direction, which is that our original set of functions have to be linearly independent. So this is a very useful tool. So let me indicate some other facts about this. Suppose we do the following example. So I'm going to consider the functions f of x equals cosine of x and g of x equals sine of x. And what I want to know is f and g linearly, are they linearly independent as elements of, say, C1 of AB? So are f and g linearly independent as elements of C1, say -1 to +1. Well, here's how we can figure that out. We can write down the Wronskian. And the Wronskian of f and g is going to be equal to the determinant. Actually, maybe I'll write it like this. Of f, g, f prime, g prime. And this will be the same thing as the determinant of cosine x, sine x. And then down here, I'm going to have the derivative of f, which is, of course, negative sine x. And down here, I'll have the derivative of g, which is just cosine of x. And so this determinant right here is the same as cosine squared of x plus sine squared of x, which will just be equal to 1. So given that this is true, we see that the Wronskian is always equal to 1. So since the Wronskian of f and g is not equal to 0, f and g are linearly independent. Let's do another example. So this time I'm going to look at, say, the following functions. So I'm going to look at f of x equals 1 plus x plus 3x squared. And then I'm going to look at g of x equals, how about 2 plus 4x squared. And then I'm going to look at h of x equals 1 minus 6 of x. And then finally, I'll look at k of x. And this will be equal to 1 plus x squared. All three of these functions have two derivatives, at least. In fact, they have infinitely many derivatives because they're polynomials. So we can regard them as elements of this vector space. And the question is, are they linearly independent? Well, to figure that out, what I can do is I can look at the following Wronskian. Actually, how would I regard them as living in here? Because I have four things, and they all have three derivatives. This is a little better. So I'm going to look at the Wronskian of f, g, h, and k. And this is going to be f, g, h, k, f prime, g prime, h prime, k prime, f double prime, g double prime, h double prime, k double prime, f triple prime, g triple prime, h triple prime, and k triple prime. And I want to take the determinant of this. Well, this is the same thing as taking the determinant of the following matrix. So for f here, I have 1 plus x plus 3x squared. Its first derivative is 1 plus 6x. Its second derivative is 6. Its third derivative is 0. Now, I now look at 2 plus x squared. Its first derivative is, 2 plus 4x squared. Its first derivative is 8x. Its second derivative is 0. Its third derivative is 0. Now I look at 1 minus 6x, its third derivative here should have been 8. And for 1 minus 6x, its first derivative is negative 6. Its second derivative is 0, and its third derivative is 0. And then finally, we look at 1 plus x squared. Its first derivative is 2x. Its second derivative is 2, and its third derivative is 0. So I've computed the associated matrix, and I can attempt to compute its determinant. But I can easily see that because I have a row here that's completely 0, the determinant of this matrix is in fact going to be equal to 0. So this suggests that these four functions are linearly dependent, not linearly independent. Now, it doesn't guarantee it, but you can in fact note that, if you take a linear combination of g and k, you can express the constant, a non-zero constant in terms of them. You can use that constant with h to express x as a non-zero constant. And likewise, you can use the constant in g to express x squared in terms of those three functions. And thus, you can express f in terms of g, h, and k. So this is a bit of a tedious calculation. I'm not going to do it. But here, already from this calculation of the Wronskian, we see that it's suggestive of the fact that these four functions are linearly dependent. But I want to indicate at least one thing that can go wrong. So here's something that can go wrong. Consider the following two functions: x squared and the square root of x times x. Well, these are both elements of C1 of the interval -1 to 1. And we can attempt to see if they are linearly independent by computing the Wronskian. So what we do is we call this F, we call this G, and the Wronskian of F and G is going to be the determinant of the following matrix. We'll have x squared here, absolute value of x here, times x here. The derivative of x squared is 2x. And the derivative of this, well, the derivative of this times this is going to be equal to, let me think for a second. So that because this function is slightly complicated, it just turns out to be 2 times the absolute value of x. So you can put that here. So note then that this is the same as x squared times 2 times the absolute value of x minus the absolute value of x times 2x, which is equal to 0. So here we see that the Wronskian is 0, which would suggest that f and g here are linearly independent. But the problem is, or they're linearly dependent, but the problem is that's not true. Even though the Wronskian vanishes, we have even though the Wronskian vanishes, we have that f and g are linearly independent. So I should show you guys why this is true. Let's suppose that there's a linear relation between f and g. Say c1 times x squared plus c2 times the absolute value of x times x is equal to 0. I can evaluate this at multiple points. Namely, I can evaluate it at 1. If I evaluate it at 1, I get c1 times 1 squared plus c2 times 1 is equal to 0, which tells us that c1 plus c2 is just equal to 0. But I can also evaluate it at -1. So I can take x here to be -1. In this case, I get c1 times -1 squared plus c2 times the absolute value of -1 times -1 is equal to 0, which is the same thing as c1 minus c2 is equal to 0. So I have this relation between c1 and c2, and this relation between c1 and c2. So you can solve this system right here, and if you do, what you learn is that the only solutions to this system are exactly c1 and c2 both equal to 0. So in fact, these relations, or these functions f and g, are linearly independent even though their Wronskian vanishes. So this illustrates some of the things that can go wrong when you're considering Wronskians. Okay, so I want to state one more theorem. It's very, very useful. Let's suppose that v1 through vn are vectors in a vector space V. Then a vector V is an element of the span from v1 to vn. Or let's suppose V is a vector in the span. Then it can be written uniquely as a combination of v1 through vn if and only if v1 through vn are linearly independent. So this will be the next thing we prove. So to prove this, let's break it into two parts. We'll have the if direction and the only if direction. So, suppose v1 through vn are linearly independent, and let's suppose we can write V as a linear combination of v1 through vn in two different ways. I'm not saying they're two distinct ways, but at least in two ways. So we can write V as alpha 1 v1 plus alpha 2 times v2 plus blah 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 alpha n vn, and so we also write it as beta 1 v1 plus beta 2 v2 plus blah 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 beta n vn. Then what happens is that we can take the difference of this relation with this relation, and we find that 0 is equal to alpha 1 minus beta 1 times v1 plus alpha n minus beta n times vn. And now this is a linear combination, or this right here is a linear combination of v1 through vn. And we've assumed that v1 through vn are linearly independent, and this linear combination is equal to 0. So by the combination of this assumption with this equation, we find that alpha I minus beta I has to be equal to 0 for all I, which means alpha I is equal to beta I. And these two expressions of V are in fact the same. So when v1 through vn are linearly independent, then your vector V can be expressed in terms of these n vectors uniquely. Now let's do the only if direction. Suppose V can be written uniquely as a combination of v1 through vn. So say we write V is equal to alpha 1 v1 plus blah 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 alpha n times vn. If v1 through vn are not linearly independent, then we also get 0 is equal to c1 v1 plus blah 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 cn times vn, where not all these ci's are equal to 0. But what we can do is we can take this relation and this relation, we can add them together. If we do that, we get V is also equal to alpha 1 plus C1 times V1 plus blah, 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 alpha n plus Cn times Vn. But because all these CI's are not equal to 0, this is a different expression than this. But that's a problem because it contradicts this assumption. We assumed V could be written uniquely in terms of V1 through Vn. And so we obtain a contradiction. Thus, both of these statements cannot be true. So if V can be written uniquely as a combination of these n vectors, then V1 through Vn, by necessity, must be linearly independent. And that completes the proof of this theorem. Okay. So now that I have done all this, I can give you guys a big, important definition, and one that will be important for the remainder of this course. And this is the notion of a basis. Given n vectors, v1 through vn, we say that they form a basis for a vector space if and only if v1 through vn are linearly independent and v1 through vn span v. So, let me start by giving you guys an example. Let's look at the vectors e1, e2, and e3 that I defined earlier. Well, last class, I proved that the span of these three vectors is precisely all of R3. And it's very easy to observe that they're linearly independent. Or all you really do is you arrange them into a matrix and you get the identity matrix. But the identity matrix has determinant 1. So because that's true, they have to be linearly independent. So not only is the span of these three vectors equal to R3, but they're linearly independent. So E1, E2, and E3 form a basis. Now here's the real important reason that we care about bases. I won't prove it today, but I at least want to state it for you guys. Suppose V1 through Vn and U1 through Un are both bases of a vector space V. Then n is equal to m. Why is that important? Because if the basis of a vector space determines a unique number, and that number is independent of your choice of basis, then this in fact leads to the following definition, which we'll do next time. And it's going to be the dimension of the vector space V. And so in my lecture on Friday, the one thing I was kind of, skirting past is I was using the notion of dimension in an unrigorous kind of moral way. But now that we have the notion of span and linear independence, we can make it all precise. And I will do that next class, and we'll work out some of the... Actually, I'm sorry, next class is the exam. That's on Wednesday. It'll be in class. So the class after that, I will work out the basics of how we use bases and all their associated utility. Anyways, that leads us to the exam. That will happen Wednesday. And it will be in class, so an hour, 30 minutes. I will do it through Zoom. This way I can kind of proctor all of you. You'll need to have your webcam turned on. I want you to take the exam. You're allowed to use like a ordinary science calculator to help you. And after you finish the exam, you can either scan your exam or you can take a picture with your phone of each of the individual pages. You'll then bake them into some sort of PDF and you'll upload it on eCampus, and we'll talk about that before the exam on Friday. Or on Wednesday. I'm sorry, Wednesday is the exam. And Friday I'll continue with this. So that's all I have for you today. Do any of you have any questions on the exam? If not, then I'm going to end it for today and go into office hours. And if any of you guys want to talk to me, I will be available on Discord. All you have to do is send me a DM and I will hop in voice chat with you. So feel free to ask me any questions about the exam in private, and I guess that's it for now. Oh, crap. I'm sorry. I keep forgetting. Sorry. You're right. The exam is the 26th. So. You're right. The exam's Friday. Next class, I will actually talk more about bases. Okay, so I'm sorry about that. I am so bad with dates, you have no idea. We will have the exam Friday. So thank you. And that'll be it for today. I'll do a review session Thursday night. It'll be at 8. It'll probably run for 3 hours. I'll announce it all on Discord. So that's all for now.